Our next scheduling policy is shortest job first. That means if we schedule our shortest job first, then overall waiting time, overall turnaround time and overall response time can be minimized, right? But again there is issue with it. How we will decide that which process is the shortest? That means beforehand we need its burst time or the burst time of each process, but we cannot predict that what can be the burst time of a process, right? We don't know. If a user submits a process, it never submit the time duration for which this process will be executed. Suppose you just open your Microsoft Office Word. Do you enter for how long you are going to work in this process? No. Suppose you open Windows Media Player. Do you enter some time that after what time you will close this process? No. So operating system will not be able to get the exact time duration of a process, and if I don't have the time duration or the CPU burst time of a process, how can I find out the shortest job? So in practical it is very difficult or almost impossible to get the burst time of all processes, and hence shortest job first scheduling algorithm cannot be implemented fully in the practical scenario, in the real life scenario, right? So CPU burst of processes used to schedule them. Two schemes are there. One is non-preemptive. Once CPU gives to the process, it cannot be preempted until completes its CPU burst. So a process which is in the running state cannot be preempted by other process while its execution is going on, right? Another scheme is preemptive. If a new process arrives with the CPU burst length less than remaining time of the currently executing process, preempt it, right? So this scheme is also known as shortest remaining time first. So SRTF is equal to SJR plus preemption, right? So when a new process with small CPU burst cycle is submitted to the ready queue, so this process will preempt the one which is executing in the CPU, and this scheme is called as preemptive shortest job first or shortest remaining time first scheme, right? SJF is optimal. It gives minimum average waiting time for a given set of processes. So we can use this scheduling process as a benchmark for all the other remaining processes. We can judge the performance of any scheduling algorithm according to SJF scheduling algorithm, right? It is hard to implement in real-time systems. Let's have an example to understand it. We have four processes with us: P1, P2, P3, P4, and their arrival time are 0.04 P1, 2.04 P2, 4.04 P3, and 5.04 P4. and their burst time are 7, 4, 1, 4 respectively. Fine. Then it is asking that draw the Gantt chart for this system and calculate average waiting time, average turnaround time and average response time using SJF non-preemptive scheme. Right? So SJF non-preemptive scheme says that when a process is executing, it cannot be preempted by other process even if that other process is having less CPU burst time than the one which is in execution state, right? So Gantt chart of this given system can look like this, right? Now you can say that the burst time of P3 is smallest, that is 1. So P3 has to execute first, but here we are executing P1 first. Why? Because at time 0 only P1 is there. At time 0 only process P1 is available in the system, right? At present we cannot say कि after 4th second process P3 will come which will be having burst time 1, right? So at this particular moment at time 0 there is only one process P1 in the system. So obviously this P1 process will be executed first. So P1 will be executed first, and again you can say that now at time 2.0 P2 is available. So at time 2 P1's remaining burst time is 7 minus 2 because 2 seconds it already completed. So remaining time duration of P1 is 5 seconds, and that is greater than P2's burst time. So P2 is having highest priority because the less burst time of P2, but P1 will not be able to preempt it by P2. Why? Because it is non-preemptive SJF algorithm scheme. So because of this, even if P2 is having higher priority than P1 or P2 is having less CPU burst time than P1, still P2 will not be able to preempt P1. So P1 will finish its execution first at 7 second, and at 7 second again check for available processes. So at the starting of 7 second you are having P2 that is arrived at 2 seconds, P3 arrived at 4 seconds, and even P4 is there that was arrived at 5th second. So at 7th second you are having P2, P3 and P4 with you, right? Now you compare the smallest burst time among these processes. So among these P2, P3, P4, P3 is having the smallest burst time of 1 second. So now P3 will be executed. P3 will be executed for 1 second, and at time 8 you will be having P2 and P3 with you. So out of P2 and P2 and P4, P3 is completed, right? So at 8 second P2 and P4 is there, and out of P2 and P4 both of them are having same burst time. So how to remove this conflict? So next priority can be their arrival time. The one which is arrived first will be executed first. So hence P2 will be executed first at 8th its burst time is 4 seconds, so it will complete its execution at 12 seconds, and then P4 will be executed after 12 seconds and it will finish at 16th second. So this is the Gantt chart of this given system. So average waiting time is equal to waiting time of process P1, that is 0, arrived at 0 and got the CPU at time 0, plus waiting time of P2. P2 was arrived at 2 seconds and it got the CPU at 8 seconds. So it has waited from 2 to 8, that is 6 seconds, right? P3 arrived at 4 seconds and it got the CPU at 7 seconds. So its waiting time is 7 minus 4, that is 3. For P4, P4 arrived at 5 seconds and it got the CPU at 12 seconds. So 12 minus 5, 7 is the waiting time of P4. So average waiting time is 0 plus 6 plus 3 plus 7 divided by 4, that is 4. Average turnaround time. So average turnaround time is equal to turnaround time of P1. So P1 was completed at 7 and it was submitted at time 0. So 7 minus 0 is turnaround time of P1. Then for P2, P2 completed at 12 and submitted at time 2. So its turnaround time is 12 minus 2, plus for P3 completed at time 8 and submitted at time 4. So 8 minus 4, that for P4 is completed at 16, submitted at 5. So 16 minus 5 divided by 4 is equal to 8. Average response time. P1's response time is 0, submitted at 0, got the CPU at time 0, plus for P2 got the first time CPU at time 8 and it was submitted at 2, so 8 minus 2, plus P3 7 minus 4 plus P4 12 minus 5 divided by 4 equal to 4, right? So you can compare here average waiting time and average turnaround time and response time with your FCFS algorithm, right? If you execute this system with FCFS, definitely this time will be greater than SJF algorithm for FCFS, right? Another example is the same process set is given, but this time they are asking to implement SJF with preemptive scheme or SRTF algorithm, right? So in this case, what can be the Gantt chart? So process P1 was executed first because at time 0 only process P1 was there. So P1 will be executed at 0.0. At 2.0 process P2 was submitted, right, which is having burst time 4, and at time 2 P1's left burst time is 5 seconds because 2 seconds it has completed, so remaining is 5 seconds. P2's burst time is smaller than P1's burst time, hence P1 is having high priority than P1, P2 is having high priority than P1. So P2 will preempt the running process P1 at time 2. So P2 will be having high priority than P1. So P2 will preempt P1 at time 2, right? At time 4 a new process P3 is submitted. So up to 4, P2 has completed 2 time units. It has started from 2. So up to 4 it has completed 2 units. So remaining burst time of P2 is 2 units and P3's burst time is 1 unit. So again P3 is having high priority than P2. So P3 will preempt process P2 at time 4. So P3 will preempt process P2 at time 4 and its burst time is 1 unit. So it will be completed at 5. At 5, P4 is submitted, which is having burst time 4. P2 is there, which is having 2 units left burst time, and P1's burst time is 5 units because 2 units it has completed and left burst time of P1 is 5 units. So P1 is having 5 units, P2 is having 2 units, P4 is having 4 units. So out of these 3 processes P1, P2, P4, P2 is having smallest burst time, that is 2 units. So next time after P3, P2 will continue, right? So after P3, P2 will continue from 5 to 7. Then P1 is having burst time 5 remaining, P4 is having burst time 4 remaining. So out of P1 and P4, P4 is having less burst time, that is 4. So P4 will be executed and then at the end P1 will be executed, right? So you can say this is how these processes will be scheduled on the CPU. So this shows the timeline diagram of the CPU, that at what time which process will be executing in the CPU, right? So average waiting time is equal to waiting time of P1, that is in the starting it has waited for 0 second, then at time 2 it left the CPU and P1 process got CPU again at 11 second. So from 2 to 11 P1 was waiting, right? So in the starting it waited for 0 second and after second it got CPU again at 11 second. So 11 minus 2, 9 second. Overall this process P1 is waited, right? For P2, first time P2 was submitted at time 2, it got CPU at time 2. So 0 second it has waited in the starting, then it went out from CPU at time 4 and again got the CPU at time 5. So 5 minus 4, 1 second overall P2 has waited. P3 submitted at time 4, got the CPU at 4 and then after it has waited for 0 second, right? For P4 submitted at time 5, got the CPU at 7, so 7 minus 5, that is 2, divided by 4 equal to 3, right? Average turnaround time of process P1 was completed at time 16. P1 was completed at time 16 and submitted at time 0. So 16 minus 0. P2 is finished at time 7 or completed at time 7, submitted at time 2. So 7 minus 2 is turnaround time of P2. P3 is completed at time 5 and submitted at time 4. So its turnaround time is 5 minus 4 plus P4 completed at time 11 and submitted at time 5. So 11 minus 5 divided by 4 is equal to 7. So this is the average turnaround time of this system. Average response time for process P1, response time is submitted at time 0, and first time it got the CPU at 0, right? So response time for P1 is 0 plus P2 was submitted at time 2 and it got the CPU at time 2. So again response time of P2 is 0. P3 submitted at time 4 and got the CPU at time 4. So its waiting time is again response time is again 0 plus P4 was submitted at time 5 and got the CPU at time 7. So its response time is 7 minus 5, that is 2. So that overall response time is equal to 0.5. So preemptive SJF performs better than non-preemptive SJF. You can compare. Waiting time here comes out to be 3, turnaround time comes out to be 7, and that of non-preemptive it was 4 was the average waiting time and 8 was the average turnaround time, and response time is 4, right? So preemptive SJF performs better than non-preemptive SJF. Here is the method by which next CPU burst cycle can be determined. Exact CPU cycle we cannot determine, but expected CPU burst time can be calculated with the help of this formula. And what is that? We are saying that Tn is equal to actual length of nth CPU burst. Tau n plus 1 is equal to predicted value for the next CPU burst. Alpha lies between 0 and 1. So the next CPU burst value can be predicted as tau n plus 1 is equal to alpha times Tn, that is the CPU burst length in nth second, plus 1 minus alpha times the predicted value in the nth second, right? So in nth plus 1 the expected value is depending on the expected or the predicted value and the actual value of the nth CPU cycle, right? So alpha Tn plus 1 minus alpha tau n will give you the next expected or next predicted CPU burst cycle, right? Here we have an example. So Ti is given as 4, 6, 4, 13, 13, 13, and they calculated tau is equal to 10, 8, 6, 5, 9, 11, 12 and so on, right? So using this formula we can calculate the predicted value of next CPU burst, right? So this is an example. Suppose we have a pattern of burst time as 6, 4, 6, 4, 13, 13, 13 and assume the initial guess is 10. Predict the next burst time alpha equal to 0.8, right? So we have tau n plus 1 is equal to alpha Tn plus 1 minus alpha tau n, where alpha is 0.8, that is given, and Tn given was 6 initially and tau n given was 10 initially. It is saying that assume the initial guess is 10, that is the tau n, and Tn initially is 6, So tau n plus 1 is equal to alpha, that is 0.8, Tn, that is 6, plus 1 minus 0.8 into 10. So this comes out to be 6.8. Now next time, tau n plus 1 is equal to alpha, Tn becomes 4, 1 minus alpha, tau n becomes 6.8, right? And you will be able to find out the next tau n plus 1, that comes out to be 4.56. So these are the expected next CPU burst cycle, and accordingly we can select the minimum CPU burst for our process. But again, this is the predicted value, it is not the exact value.